In the vast, silent cosmos, an extraordinary event is unfolding. 7 massive comets, ice-bound wanderers from the outer solar system, are racing toward the Sun, all arriving within days of each other in October 2025. Their tails stretch millions of miles like glowing streams slicing through the void. At the same time, an interstellar visitor, 3 Atlas, is making its closest approach to our star. The odds of this convergence are staggering, like predicting 7 grains of sand to collide simultaneously. So before we go deeper, hit like, subscribe, and tell me in the comments what you think this really means. And if you want to help this message reach others who still wonder, share it. On X, Facebook, Reddit, or even just in your group chats. You're the reason this search is alive. Thank you for keeping your eyes open. Is this mere coincidence or something more intentional? These comets, speeding at over 150,000 miles per hour, have travelled for millennia from the icy Oort cloud. Where the Sun is just another bright star, now their surfaces vaporize under solar heat, releasing gases and dust that form brilliant tails. Astronomers worldwide are mobilizing telescopes, including Hubble and James Webb, to document this phenomenon. 3 Atlas, the first interstellar object since Oumuamua in 2017 and Borisov in 2019, adds to the enigma. Its trajectory hints at eons of galactic travel, and its composition remains a mystery. Is it a rocky asteroid, an icy comet, or something else entirely? Its arrival alongside the comets defies statistical probability, fueling speculation about unseen forces or even intelligent design. Tonight, we embark on a journey to unravel this celestial mystery, tracing trails of ice and dust and exploring the invisible forces shaping their paths. From the frost-covered peaks of Mauna Kea to the dusty archives of ancient texts, we'll search for clues. We'll examine cutting-edge theories from astrophysicists who question whether this convergence is natural or something more profound. By the end, we'll uncover what 3 Atlas is truly doing to our solar system and what it means for our future among the stars. Is it a passive traveller or a catalyst for something greater? The answers may redefine our understanding of the cosmos and our place within it. Part 1. The Celestial Parade. In 2025, a remarkable event will occur. 7 comets, termed the Dwarf Effect, will align in the night sky within a short window. Last seen in 1106, this phenomenon inspired both wonder and fear. This time, state-of-the-art telescopes, like Chile's Large Synoptic Survey Telescope, LSST, will capture it in unparalleled detail. In late June 2025, Lee, the first comet, will streak across the sky, its ionized blue tail glowing. A week later, Ordway will join, their paths visibly intersecting. By mid-July, 5 more comets, Harmon, Sterling, Edmonds, Clark and Bertram, will brighten the sky, outshining the full moon. The odds of such clustering are estimated at 1 in 10 billion. What triggers this rare alignment? Theories range from the gravitational pull of an undiscovered Planet 9 to the idea that these comets are fragments of an ancient body. Others suggest a cyclical event tied to hidden solar system dynamics. Unraveling this mystery requires studying the comets and the forces guiding them. The comets are diverse. Lee, the smallest, has a 2-kilometre nucleus but a tail stretching over 10 million kilometres. Ordway, the largest, spans over 15 kilometres, with craters and vents releasing water vapour and organics. Their tails hold clues to their origins. Lee's tail, rich in carbon monoxide, points to formation in the outer solar system. Ordway's tail with water ice and complex organics suggests a warmer birthplace. Observation: the comet's tails reveal their chemical makeup and origins. Speculation: could they be remnants of a disrupted Oort cloud, propelled inward by a rogue planet or passing star? If so, the 2025 parade may signal a longer cosmic event. As the comets near, their gravitational effects are felt on Earth. Tides rise slightly higher, satellites face minor. Disruptions and the International Space Station requires added thrust to maintain orbit. Stargazers worldwide gather, sharing breathtaking images that saturate social media. Schools integrate the event into science curricula and cities host rooftop viewing parties. The Celestial Parade is more than a spectacle, it's a scientific goldmine. Comets are time capsules from the early solar system, and studying them could unveil secrets of planetary formation. And life's origins. Early analyses already show the presence of amino acids and complex organics, supporting the theory that comets delivered life's building blocks to Earth during the late heavy bombardment. Interpretation: the 2025 parade offers a glimpse into the solar system's past and future. The comet's synchronized arrival hints at a deeper cosmic order. As they continue their journey, their paths will diverge, influenced by planetary gravitational forces. Some may return in centuries, others may vanish forever. But for a brief moment in 2025, they will remind us of our place in the universe. As summer 2025 ends, the comets will fade, their tails dissipating. For astronomers, the work will just begin, with years of analysis ahead. For the rest of us, the comets will leave a sense of awe and a reminder that the universe still holds mysteries beyond our understanding. We await the next parade, the next glimpse into the celestial dance that has captivated humanity for millennia. Part 2. The Cosmic Cast. Imagine a lineup of suspects, each with their own alibi, but all arriving at the same crime scene. Meet the 7 comets of 2025: Pan-STARRS, Swan, Stereo, Atlas K1, Atlas G3, Lemon, and Neat. Each carries a unique story of discovery and a cosmic journey spanning millions of years. Pan-STARRS, the brightest of the group, promises naked-eye visibility for lucky observers, its coma glowing like a ghostly apparition against the night sky. Its tail stretches. Across the heavens, a luminous streak painted by the solar wind, visible even from urban skies. Swan, detected by its hydrogen glow, was already outgassing long before its discovery, trailing a faint, ethereal veil of ionized gas that stretches over 10 million kilometers. Its chemical signature, rich in hydroxyl and hydrogen compounds, suggests it has been active for decades, long before human eyes turned its way. Stereo, a potential solar grazer, dives toward the sun during a period of heightened solar activity, its icy surface boiling under the relentless heat. Its trajectory brings it within 1.5 million kilometers of the solar surface, close enough for its tail to be violently disrupted by the sun's magnetic field. This dance with the sun could strip away layers of its nucleus, revealing primordial material untouched since the birth of the solar system. Atlas K1 and Atlas G3, siblings in name but not in origin, were discovered by the same survey yet follow wildly different orbits. K1, a long-period comet, likely originated in the distant Oort cloud, while G3, a Jupiter family comet, has a more compact orbit shaped by the gas giant's gravitational influence. Their dual presence raises questions about the interplay between distant and nearby reservoirs of cometary material. Lemon, named for the Australian observatory that first spotted. It is a dynamic enigma. Its orbit is highly inclined, tilting it at a steep angle relative to the plane of the solar system. This suggests its origins lie far beyond the influence of the planets, in the chaotic outer reaches of the Oort cloud. Its brightness has fluctuated unpredictably, hinting at an unstable nucleus prone to outbursts of gas and dust. Neat, the smallest of the group, is a fragment of a larger comet that shattered centuries ago. Its diminutive size makes it vulnerable to rapid disintegration as it approaches the Sun, a fate shared by countless comets before it. Yet its very fragility makes it a precious time capsule, its icy core preserving the chemical fingerprints of the early solar system. Yet their stories converge in a way that feels almost coordinated. 7 comets, discovered by different surveys using different methods, all arriving at the same cosmic party. The pattern is undeniable, but the explanation remains elusive. Are these objects truly independent travelers, or are they part of a larger, unseen choreography? The odds of such a clustering occurring by chance are astronomically low, estimated at less than 1 in a million. Yet no plausible mechanism has been proposed to explain how these comets could be influenced to arrive in unison. Some researchers speculate about the gravitational influence of an undiscovered planet or a distant stellar encounter, while others suggest the clustering is a statistical fluke, a once-in-a-lifetime alignment of celestial gears. Observation. The 7 comets exhibit a range of orbital characteristics, with inclinations spanning from 12 to 90 degrees, and periods ranging from 5 to over 1,000 years. Their diverse chemical compositions suggest they originated from different regions of the solar system, some from the Kuiper Belt and others from the distant Oort cloud. Interpretation. Their convergence could be the result of a complex interplay of gravitational forces, including perturbations from the outer planets and the cumulative effects of stellar passages over millions of years. Alternatively, it may be a coincidence amplified by the increasing sensitivity of modern comet surveys, which are detecting fainter and more distant objects than ever before. Speculation. Could this clustering be the first observable evidence of a larger, unseen structure in the outer solar system, such as a dense band of cometary material or the gravitational wake of a rogue planet? Or is it a harbinger of a new era in solar system dynamics, where human observation and cosmic serendipity align to reveal patterns previously hidden in the chaos of celestial motion? What we know: 7 comets are approaching perihelion. Within days of each other, their orbits are consistent with natural gravitational evolution, with no evidence of artificial manipulation. The comets vary widely in size, brightness, and composition, reflecting their diverse origins. What we don't know: why this clustering is occurring now, and whether it's more than coincidence. The long-term implications of this event remain uncertain, but it offers a rare opportunity to study the behavior of multiple comets in close proximity, potentially shedding light on their formation and evolution. Part 3. The Outlier. While our 7 comets dance their predictable orbits, something else stalks the darkness between the planets. 3 Atlas, the third confirmed interstellar object ever detected in our solar system, is passing through on a one-time hyperbolic trajectory. Unlike our comet-welcoming committee, this visitor wasn't born here. It formed around another star, carrying ice and dust seasoned by millions of years of cosmic radiation. Its surface, pitted and ancient, bears the scars of a journey that began in the distant reaches of the galaxy, perhaps as far as 500 light-years away. Moving at an astonishing speed of over 100,000 kilometers per hour, 3 Atlas is a lonely traveller, a cosmic nomad that will never return once it exits our solar system. The timing of 3 Atlas's arrival raises uncomfortable questions. Is it pure coincidence that our solar system's most unusual comet year coincides with a visit from an interstellar stranger, or could there be something more deliberate at work? As we trace the paths of our 7 comets, we must also ask, is 3 Atlas a silent observer, or is it somehow connected to their synchronized arrival? Its trajectory, when plotted against the orbits of the comets, reveals no obvious intersection, yet the proximity of its flyby to the comet's perihelion dates is unsettlingly close. Some astronomers have calculated that the probability of such a coincidence is less than 1 in a million, a statistical outlier that defies easy explanation. Observation: 3 Atlas is not the first interstellar visitor to grace our solar system. In 2017, Oumuamua, a cigar-shaped object, puzzled scientists with its bizarre shape and unexpected acceleration as it left our solar system. 2 years later, Borisov, a more comet-like interstellar object, arrived, its tail of gas and dust streaming behind it like a cosmic banner. Yet, 3 Atlas is unique in its timing and trajectory, arriving during a year when 7 comets, all with orbital periods ranging from 200 to 400 years, are converging in a rare celestial alignment. Interpretation: the arrival of 3 Atlas during this unprecedented comet year could be a mere coincidence, a quirk of celestial mechanics. However, the improbability of the event has led some researchers to propose more speculative theories. Could 3 Atlas have been influenced by an unseen gravitational force, nudging it into our solar system at precisely this moment? Or is it possible that this interstellar object is not a natural phenomenon, but an artifact, a probe sent by an advanced civilization to observe our solar system during this unusual event? Speculation: if 3 Atlas is indeed an artifact, its purpose remains unclear. Is it a passive observer collecting data on the comets in our solar system before continuing its journey through the cosmos? Or could it be something more sinister, a harbinger of change, a catalyst for cosmic events yet unseen? Its composition, rich in heavy metals and complex organic compounds, hints at the possibility of an advanced manufacturing process, though natural explanations have not been ruled out. As it speeds away from us, 3 Atlas leaves behind more questions than answers, a lingering enigma in the vastness of space. Yet, even if 3 Atlas is a natural object, its presence is a reminder of our cosmic neighborhood's complexity. Every interstellar visitor brings with it a piece of the galaxy, a fragment of the cosmic story written in ice and dust. As we study 3 Atlas, we are not just observing an object, but deciphering a message, a whisper from the stars that speaks of distant worlds and ancient histories. Its journey through our solar system is a fleeting moment, a cosmic handshake between 2 star systems billions of miles apart. And as it disappears into the void, it carries with it the story of our comets, their synchronized dance forever etched in its icy memory. Part 4. The Unseen Hand. When astronomers confront the unexplained, they turn to 2 fundamental forces, gravity and electromagnetism. If something is guiding comets into synchronized arrivals, it must act through one of these mechanisms. Gravity shapes every orbit, but its influence is weak, requiring massive objects to exert noticeable effects. To tug on a comet would necessitate something monumental, a planet, a star, or an unknown entity. Could a hidden gravitational shepherd be nudging these comets into alignment, The idea of an unseen hand guiding celestial bodies is not new. In the 19th century, astronomers proposed the planet Vulcan to explain Mercury's peculiar orbit. Though never found, the concept of invisible influences persists. The 20th century brought the discovery of dark matter comprising 27% of the universe, and the hypothetical Planet 9, proposed in 2016, which could explain clustered orbits. In the Kuiper Belt, if such a world exists, its gravitational reach could subtly bend comet trajectories. Yet, even Planet 9's estimated mass would struggle to synchronize 7 comets across vast distances. Observation: if such an object exists, its influence should be detectable in the comet's orbital characteristics. However, their paths reveal no obvious perturbations. Each comet adheres to Newtonian mechanics, shaped by the sun's gravity. And occasional planetary nudges. Their orbits vary wildly, from steep inclinations to near circular paths. No single gravitational source seems capable of harmonizing such disparate trajectories. Interpretation: so far, each comet follows an independent path shaped by known gravitational forces. The Oort cloud provides a steady stream of comets, dislodged by passing stars or galactic tides, which should careen toward the sun in chaotic fashion. Their arrival times and trajectories should be random. Yet these 7 comets defy that randomness, hinting at an underlying order. If gravity isn't the culprit, perhaps electromagnetism holds the key. The solar system is awash in electromagnetic forces. The sun's magnetic field stretches billions of kilometers, its tendrils sweeping past planets and comets. Solar winds exert gentle pressure on anything in their path. For comets, this interaction creates their iconic tails. But could this interplay also alter a comet's trajectory? The effect is minuscule compared to the sun's gravitational pull, but over time, even the smallest force could accumulate, nudging comets into alignment. Speculation: could 3 Atlas, despite its small mass, influence these objects through unknown mechanisms? Its behavior already defies cometary physics. If 3 Atlas is not a comet but something else, a remnant, or an artifact, its capabilities could far exceed our understanding. Perhaps it emits electromagnetic pulses or possesses exotic matter, exerting a gravitational pull disproportionate to its size. As we stare into the abyss, the possibilities seem endless. But there's another possibility. What if the unseen hand isn't an object at all, but a pattern, a cosmic coincidence masquerading as design? The universe is full of such illusions. Could these 7 comets be another trick of perspective? Their synchronized arrivals nothing more than a fluke. The odds seem astronomical, yet the universe has a way of defying expectations. As we probe deeper into this mystery, one question lingers. Are we witnessing the handiwork of nature, or the whispers of something far stranger? Part 5. The Alarm. The alarm isn't a warning of immediate danger, but a call to investigate an unusual celestial pattern. In 2025, the skies will fill with spectacle as multiple bright comets develop spectacular tails simultaneously. This will inspire awe, spark renewed interest in astronomy, and boost telescope sales by over 300%. Schools and communities will gather to watch the night sky transform into a canvas of streaking light. However, the spectacle isn't the cause of the alarm. Comets are fragile and pose no direct threat, their orbits stable and well studied. The nearest, C2025 K1, will pass within 0.3 astronomical units of Earth, over 100 times the distance to the Moon. The real alarm stems from the unusual arrival of 7 comets at once. While comets often travel in clusters, these groups typically arrive over decades or centuries. The 2025 comets have no common origin. Their orbits are distinct. Their compositions varied. This defies our understanding of cometary dynamics. Observation. 7 comets arriving simultaneously in 2025 is unprecedented. Preliminary spectral analysis suggests that at least 3 have unusual chemical signatures, further complicating the mystery. History has shown that celestial phenomena can captivate humanity, but never have multiple independent comets arrived in such close proximity, their tails synchronizing. Like a cosmic ballet, speculation. Could this be a natural fluke or a more deliberate phenomenon? The idea of comets being influenced by external forces isn't far-fetched. In 2017, Oumuamua raised questions with its unusual trajectory. Similarly, the 2025 comets raise questions about their origin and behavior. Some researchers suggest a gravitational lens effect caused by an unseen mass, though no evidence supports this theory. The synchronized. Tails glowing in the ultraviolet spectrum have led some to suggest an unknown energy source influencing their behavior. The scientific community is divided between chance occurrence and a guided hand. Public imagination will run wild, with theories ranging from doom to cosmic welcome signs. Regardless, the 2025 comets will capture global attention and spark conversations about our place in the universe. Astronomers will study their composition and track their movements using technology like the James Webb Space Telescope. Space agencies will launch probes to collect samples, potentially unlocking secrets about the early solar system. JAXA and NASA have announced plans for a joint mission to intercept one of the comets, aiming to return a sample to Earth by 2030. As the comets draw closer, so will the questions they raise. Are we alone in the universe? Are these comets a message or something else entirely? The answers, if they exist, lie in the stars, and in the hearts of those who dare to look up and wonder. The 2025 comets will be both a celestial spectacle and a cultural phenomenon, reshaping how humanity views the cosmos and its mysteries. Part 6. The Interstellar Stranger. 3 Atlas stands apart from other comets. It's an interstellar traveler, a messenger from another star system, with a hyperbolic trajectory ensuring a one-time visit to our solar system. This provides a fleeting chance to study material from a distant star, but its arrival raises pressing questions. Could this stranger be linked to the unusual timing of our 7-comet swarm? Its nucleus, estimated at just 200 meters across, glows faintly under. The scrutiny of Earth's most powerful telescopes. Designated C2023-T3, Atlas. 3 Atlas was first detected as a faint smudge by the Atlas Survey telescopes in Hawaii. Its trajectory was quickly flagged as unusual, moving too fast and strangely to originate from the Oort cloud or Kuiper belt. Its hyperbolic path indicated it had travelled through interstellar space for millions of years before entering our solar system, its surface scarred by ancient collisions and cosmic weathering. Observation. 3 Atlas's trajectory and speed of 30 kilometers per second confirm it originated beyond our solar system. Interpretation. Its arrival during an unprecedented comet year seems more than coincidental, sparking debate about potential connections. Speculation. Could 3 Atlas actively influence comet clustering, or is it just a cosmic coincidence in the grand scale of the universe? The comets. Composition hints at its interstellar origins. Spectroscopic analysis reveals high levels of iron and nickel, suggesting formation in a star system unlike ours. Its surface, darkened by cosmic rays and interstellar dust, reflects less than 5% of sunlight, making it one of the darkest objects observed in our solar system. Trailing behind it, a faint tail of ionized gas stretches over 800,000 kilometers, glowing eerily under ultraviolet light. 3. Atlas follows Oumuamua 2017 and Borisov 2019 as the third interstellar visitor. While those objects sparked debates about extraterrestrial origins, 3 Atlas is unique due to its timing. Its arrival during a year of extraordinary comet activity has led astronomers to question whether these events are truly independent. Unlike its predecessors, 3 Atlas appears to have a slightly altered trajectory, suggesting it may have interacted with another celestial body during its journey. The 7-comet swarm is highly unusual. Typically, only a few new comets are discovered yearly, but this year 7 bright comets were identified with perihelion dates within just 3 months. This clustering defies explanation, as comets are notoriously unpredictable. The odds of such an event are less than 1 in a million. Simulations suggest that a gravitational perturbation, perhaps from an undetected object, could have nudged these comets into their current paths. Observation: the comet swarm's perihelion dates fall within an improbably narrow window. Interpretation: this clustering hints at a shared cause or perturbation affecting their orbits. Speculation: could 3 Atlas have influenced this perturbation, or is its arrival unrelated, merely amplifying the swarm's significance? The scientific community is divided over a potential connection between 3 Atlas and the comet swarm. Some argue that 3 Atlas is too small to have influenced other comets' orbits, while others suggest it may possess unknown properties. Meanwhile, some dismiss the idea as mere coincidence, citing the universe's vast scale and the unpredictability of celestial mechanics. As telescopes track the swarm, subtle variations in their brightness hint at complex interactions between the comets themselves. As 3 Atlas journeys through our solar system, astronomers are racing to study it before it vanishes. Telescopes worldwide, including the James Webb Space Telescope, are capturing its every detail. Each observation deepens our understanding, but questions persist. Is 3 Atlas a harbinger of something greater, or simply a wanderer passing through? The answers may lie beyond our current knowledge, hidden in the depths of interstellar space. Its faint glow fades as it speeds toward the outer solar system, a fleeting visitor from the cosmic abyss. Part 7. Orbit of Intrigue. 3 Atlas traces a hyperbolic trajectory, indicating its interstellar origins and eventual departure from our solar system. Approaching from Perseus, it dives toward the Sun before accelerating back into interstellar space. Its path intersects the ecliptic plane, crowded with solar system debris and cometary orbits. This intersection is dynamic, with 3 Atlas encountering dust particles and ancient fragments that subtly shape its trajectory. Observation: unlike solar system comets, 3 Atlas's velocity exceeds the Sun's escape velocity by 26 kilometers per second, marking it as a traveler. Its closest approach to the Sun, or perihelion, occurs at just 0.2 astronomical units, AU, well within Mercury's orbit. This journey increases the likelihood of interactions with other objects. At perihelion, temperatures on its surface soar to over 500 degrees Celsius, causing it to shed layers of material in a process called outgassing. This creates a tenuous atmosphere, offering astronomers a fleeting chance to study its composition. Speculation. 3 Atlas's proximity to the ecliptic and intersection with cometary orbits may suggest a shared history. Ejected from distant star systems, it could be a relic shaped by alien forces. Its spectral analysis reveals traces of heavy elements like nickel and iron, rare in solar system. Comets but common near supernovae. This raises the possibility that 3 Atlas originated in a star system forged from a supernova. Interpretation. Discovered in 2023, 3 Atlas's passage coincided with the perihelion of several known comets, including 21P Chi-Giacobini-Zinner and 46P Virtanen. Though likely coincidental, this alignment offers a natural laboratory for studying the interplay between interstellar and local comets. Observations. During this period, reveal how solar forces sculpt these objects, providing insights into their evolution. 3 Atlas's hyperbolic path offers a window into the larger universe. As it accelerates back into interstellar space, it carries the imprint of our solar system, the gravitational tug of the sun, solar wind radiation, and planetary influences. Its trajectory points toward Perseus, hinting at a distant stellar nursery where similar objects may have formed. Traced backward, its path aligns with star-forming regions within Perseus, suggesting it was ejected millions of years ago. Observation. Subtle perturbations in 3 Atlas's orbit suggest unseen masses in the outer solar system. These anomalies could indicate an undiscovered planet in the Kuiper Belt or beyond. Astronomers have detected deviations in its path as small as 0.01 arc-seconds, which could be explained by a distant Earth-sized planet or a rogue gas giant. Cinematically, 3 Atlas's journey unfolds like a ballet. Approaching the sun, its surface heats, releasing gases that form a faint coma and a trailing contrail. This allows scientists to study its composition remotely, providing a rare glimpse into interstellar objects. Its coma, glowing under solar radiation, stretches across millions of kilometers, creating a transient, ethereal tale that traces its path. Interpretation. 3 Atlas's orbit tells a story of cosmic migration and interconnectedness. Its journey challenges our understanding of solar system belonging and reminds us of the universe's interwoven nature. As it recedes into the cosmic void, it leaves a legacy of discovery and a call to explore the interstellar frontier. The data collected during its brief visit will inform future missions and inspire new technologies, pushing the boundaries of human knowledge. Part 8. What happens at perihelion? Perihelion is the moment of truth for any comet, the closest approach to the sun, when months or years of gradual approach suddenly accelerate into a crescendo of activity. For 3 Atlas, this milestone is particularly significant. As an interstellar visitor, it will experience the full intensity of our star's radiation and particle output for the first time. The physics of perihelion are both predictable and dramatic, as 3 Atlas draws closer. To the sun, solar radiation intensifies, vaporizing ice that remained frozen during its long interstellar journey. At its closest approach, temperatures on the comet's surface could soar to over 300 degrees Celsius, transforming its icy exterior into a roiling, gaseous coma that stretches tens of thousands of kilometers into space. The perihelion of 3 Atlas is expected to occur at a distance of approximately 0.25 astronomical units from the Sun, well within the orbit of Mercury. This proximity subjects the comet to solar winds moving at speeds of up to 800 kilometers per second, bombarding its surface with charged particles and stripping away layers of material. The resulting outgassing could create spectacular jets of dust and gas, illuminated by the sun's glare, forming a tail that stretches millions of kilometers. This display, while visually stunning, is also a critical opportunity for scientists to analyze the composition of the comet. By studying the spectral signatures of the ejected material, researchers can determine the presence of elements like carbon, nitrogen, and oxygen, offering clues to the conditions of 3 Atlas's birthplace beyond our solar system. But what if this crescendo reveals something more? If 3 Atlas is somehow connected to our 7-comet swarm, perihelion provides the most likely window for dramatic revelations. Sudden brightness increases, jetting material, or even fragmentation could hint at forces operating beyond our current understanding. For example, if 3 Atlas were to fragment under the stress of solar heating, it would join the ranks of comets like Shoemaker-Levy 9, which famously broke apart in 1992 and collided with Jupiter 2 years later. Such an event would not only reshape our understanding of 3 Atlas, but also raise questions about the stability of interstellar objects and their potential hazards to planetary systems. As we watch 3 Atlas approach its moment of truth, we must also monitor our 7 comets for any signs of coordinated behavior. The cosmic clockwork continues its precise operation, indifferent to speculation but faithful in providing the data we need to distinguish between coincidence and causation. Observations from space-based telescopes. Like the Hubble and ground-based observatories will be essential in capturing high-resolution images and spectroscopic data. These instruments will track the comet's movements, measure their brightness, and analyze their chemical compositions, building a comprehensive dataset to compare against the behavior of 3 Atlas. Observation. If the 7 comets exhibit simultaneous changes in brightness or trajectory as 3 Atlas reaches perihelion, it would suggest an underlying connection, perhaps gravitational or even electromagnetic in nature. Such synchronization would defy conventional explanations, as comets typically follow independent paths dictated by their unique orbits and compositions. Interpretation. The perihelion event could act as a stress test for theories about the swarm's origins. If the comets respond in unison to 3 Atlas's closest approach, it might indicate a shared origin or an unseen influence binding them together. This would challenge the prevailing models of cometary behavior, which assume random and unconnected trajectories. Speculation. Could the swarm and 3 Atlas be part of a larger, undetected structure, such as a disintegrating interstellar cloud or the remnants of a shattered exoplanet? While purely hypothetical, such scenarios underscore the vast unknowns of interstellar space and the potential for new discoveries to rewrite our understanding of cosmic dynamics. As 3 Atlas hurtles toward its rendezvous with the Sun, the stakes are high and the possibilities are endless. Every measurement, every observation brings us closer to unraveling the mystery of this interstellar visitor and its potential connection to the swarm. In the furnace of perihelion, the truth, whatever it may be, will be forged. Part 9. The Swarm and the Sun. Our Sun operates on cycles that dwarf human attention spans, alternating between periods of relative calm and phases of dramatic activity. The 11-year solar cycle that governs this behavior reaches its peak in 2025, transforming our star into a more volatile and visually spectacular version of itself. During this period, the Sun's surface erupts with sunspots, dark, Earth-sized magnetic storms that serve as the engines of solar flares and coronal. Mass ejections. At its height, the solar maximum can unleash over 2,000 sunspots, compared to near zero during the solar minimum. This enhanced solar activity creates both opportunities and complications for our investigation. Solar maximum brings frequent coronal mass ejections, billion-ton bubbles of magnetized plasma hurled from the sun's corona. These shock waves can interact with comet tails, creating dramatic disconnection events and plasma. Instabilities that make even modest comets appear far more spectacular than they would during quieter solar periods. In 2007, a coronal mass ejection tore apart the tail of Comet Encke, stretching it over 20 million kilometers and producing a display visible even in small telescopes. But this same solar activity also affects Earth's magnetosphere, threatening satellite communications, GPS navigation, and even power grids. In 1989, a solar storm caused a 9-hour blackout in Quebec, affecting 6 million people and costing hundreds of millions of dollars. As we watch our 7 comets dance in the sun's fiery embrace, their tails glowing like fiery contrails against the blackness of space, we must also ask, could solar activity somehow influence their arrival timing? Solar wind and magnetic fields can subtly alter the trajectories of comets, nudging them slightly off course over time. For example, the solar wind has been observed to slow the orbital speed of some comets by as much as 10 meters per second, a seemingly small figure that translates to significant shifts over millions of kilometers. And if so, what does that tell us about the forces shaping our solar system? Observation. The comet's behavior during solar maximum may provide clues about their composition and history. Comets are often described as dirty snowballs, but they're. Responses to solar activity can reveal the proportion of ice to dust, the presence of complex organic molecules, and even the conditions of their formation billions of years ago. For instance, comet 67P Churyumov-Gerasimenko, studied by the Rosetta mission, showed that its icy nucleus was darker and more porous than expected, suggesting a violent early history of collisions and solar heating. Interpretation. The timing of the comet's arrival in relation to the solar cycle could hint at a deeper connection between solar activity and the gravitational dynamics of the Oort cloud, the distant reservoir of comets. Some theories suggest that solar cycles might influence the frequency of comet ejections from the Oort cloud, though this remains highly speculative. If true, it would imply that the sun not only shapes the behavior of comets, but also governs their origins and journeys through the solar system. Speculation. Could solar activity be a factor in the apparent clustering of comet swarms? While the gravitational influence of Jupiter and other gas giants is the primary suspect, the sun's magnetic field and solar wind could play a secondary role, subtly synchronizing the orbits of comets over millions of years. This idea, though unproven, opens the door to a more interconnected understanding of the solar system, where the sun's cycles are not just a backdrop, but an active participant in shaping the cosmic ballet of comets. As we study these celestial wanderers, we are reminded that the sun is not a passive observer, but a dynamic force, its cycles of calm and chaos shaping the story of our solar system in ways both visible and invisible. The swarm of comets glowing under the sun's relentless gaze is not just a spectacle. It is a testament to the intricate dance of gravity, magnetism and light that binds our corner of the cosmos together. Part 10. Echoes on Earth. While comets themselves are harmless, the solar activity that illuminates their tails can disrupt Earth's electronic infrastructure in profound ways. Geomagnetic storms triggered by solar particles can overload power grids and damage satellites, leaving entire regions without power or communication. In 1989, a severe storm caused a 9-hour blackout in Quebec, affecting over 6 million people and causing economic losses estimated at $2 billion. Auroras danced as far south as Texas, a vivid reminder of the sun's reach. Satellites are particularly vulnerable to these storms. During a 2003 solar event, 10% of the world's satellite fleet malfunctioned, disrupting GPS navigation, weather forecasting, and telecommunications. The financial toll was estimated at $70 billion globally, underscoring the fragility of modern technology in the face of space weather. Solar storms also shape our perception of celestial events, often blurring the lines between correlation and causation. When comet activity aligns with solar maximum conditions, as it did in 2014, the spectacle can seem more than coincidental. However, solar storms affect comets and Earth independently, each responding to different aspects of solar activity. Comets react to variations in particle density and magnetic fields, their tails glowing as solar wind strips away material. Meanwhile, Earth's infrastructure is impacted by streams of charged particles interacting with its magnetic field, leading to geomagnetic storms. The correlation exists because both phenomena share a common solar cause, not because comets influence terrestrial systems. Yet the coincidence is striking, fueling both wonder and misconceptions. The 1859 Carrington event, the most powerful solar storm on record, offers a chilling glimpse into the potential consequences of such events. Telegraph systems, the cutting-edge technology of the time, failed spectacularly. Sparks flew from machinery, shocking operators and setting papers ablaze. Auroras, typically confined to polar regions, illuminated skies as far south as Cuba and Hawaii, so bright that people mistook them for dawn. If a storm of this magnitude occurred today, the results would be catastrophic. Power grids would collapse, satellite communications would falter, and GPS systems would fail, with potential economic losses exceeding $2 trillion. Essential services like healthcare, transportation, and finance would grind to a halt, highlighting the modern world's dependence on technology vulnerable to space weather. Observation. The Sun's 11-year solar cycle, which includes solar maximums, influences the frequency and intensity of geomagnetic storms. During these periods, solar flares and coronal mass ejections, CMEs, release energy and charged particles that interact with Earth's magnetic field, disrupting infrastructure. The 7-comet swarm, while visually stunning, does not cause these disruptions. Comets, composed of ice, dust and rock, respond to solar wind and radiation, forming their iconic tails. However, they do not emit charged particles or magnetic fields that cause geomagnetic storms. For example, during the 2013 approach of Comet Ison, its tail stretched over 16 million kilometers, captivating observers. Yet it was the coinciding solar activity that caused temporary satellite disruptions, not the comet itself. Interpretation. The overlap of comet activity and solar storms can lead to misunderstandings, as people often attribute disruptions to comets, believing they have a mysterious influence. This misconception is fueled by the dramatic appearance of comets, which have long been associated with omens and superstitions. However, scientific evidence clearly shows that disruptions are caused by solar activity. During the 2014 solar maximum, comets like Ison and Lovejoy had bright tails, coinciding with geomagnetic storms and satellite anomalies. Observers speculated about comet influence, but scientists clarified that solar activity was the cause. Public education is vital to dispel such myths and ensure a clear understanding of space weather events. For instance, NASA's Space Weather Action Center's program educates students and the public about the science behind solar storms, fostering informed dialogue and reducing fear, speculation. As technology advances, so does our vulnerability to space weather. Complex power grids, satellite networks, and communication systems mean even minor disruptions can have significant impacts. A prolonged blackout from a geomagnetic storm could cripple essential services, from hospitals to water treatment facilities. To mitigate risks, governments and companies are investing in research and infrastructure to predict and protect against solar storms. Missions like NASA's Solar Dynamics Observatory and the ESA's Solar Orbiter study the sun's impacts on Earth, providing unprecedented data. Advancements in space weather forecasting could provide early warnings, allowing preventive measures to minimize damage. For example, power grids could be temporarily shut down to avoid overloads, and satellites could be repositioned to reduce exposure. Shielding satellites from solar particles is also a priority, with innovations like radiation-hardened electronics and magnetic shielding being explored. Understanding solar storms is essential for safeguarding technology and ensuring societal resilience in an increasingly interconnected world. The 7-comet swarm highlights the interconnectedness of the solar system and the delicate balance between natural phenomena and human technology. While appreciating the beauty of comets, we must recognize the unseen forces at work and prepare for the challenges they pose. By doing so, we can ensure that fascination with celestial events does not overshadow the importance of understanding and mitigating risks. After all, the same solar wind that paints comet tails can also disrupt the very systems that allow us to marvel at them. In this way, the story of comets and solar storms is not just one of celestial wonder, but of human adaptation and resilience in the face of cosmic forces. Part 11. Harbingers of Change. Throughout history, bright comets have been seen as cosmic messengers, tapping into humanity's deepest fears and aspirations. Ancient Chinese astronomers linked them to dynastic changes and disasters, meticulously documenting their appearances in texts like the records of the Grand Historian. The Han dynasty, for instance, witnessed Halley's Comet in 12 BC, where it was seen as a portent of political strife. Over a millennium later, in 1066, the comet blazed across European skies during the Norman conquest, immortalized in the Bayeux Tapestry as an omen of William the Conqueror's victory. The Great Comet of 1577, observed by astronomers like Tycho Brahe, sparked both scientific inquiry and widespread panic across Europe, as people feared it signaled divine wrath or impending apocalypse. In 2025, 7 comets converged during a time of rapid technological change and geopolitical tension. The first, C2023 V1, was discovered by an amateur astronomer in Chile, whose grainy footage of the faint smudge went viral overnight. Social media amplifies the sense of cosmic significance, with platforms like TikTok and Instagram flooded with dramatic comet videos. A 14-year-old in Mumbai gains millions of followers after posting a time-lapse of comet C2024H2, its tail stretching across the night sky like a glowing brushstroke. Independent creators. often converge on similar interpretations, creating a false consensus around unfounded ideas such as alignments with ancient Sumerian constellations or the Mayan calendar. Conspiracy theories flourish, with one viral thread claiming the comets are artificial objects sent by extraterrestrial civilizations. The comet swarm creates an unprecedented spectacle. The last time multiple comets appeared in close succession was in 1910, when 3 were visible within a single year. However, the 2025 swarm is unmatched in scale and visibility, with all 7 comets passing within 0.1 AU of Earth, closer than any comet in modern times. Astronomers calculate that the combined brightness of the comets will exceed that of a full moon, casting distinct shadows on the ground. The European Space Agency launches an emergency study mission, while NASA reassures the public that there is no collision risk, though satellite. Disruptions are possible. Amateur astronomers and scientists alike marvel at the rare opportunity to study cometary composition and behavior in such proximity. As the swarm approaches, questions arise. Are these comets truly harbingers of change, or mirrors reflecting our hopes and fears? Environmental activists in Germany adopt the comets as a symbol of their movement, projecting images of melting glaciers onto their tails during protests. Doomsday. Preppers in the US stockpile supplies, citing the comets as evidence of imminent global catastrophe. Religious leaders offer conflicting interpretations, with some claiming the comets herald the end times while others see them as divine blessings. Astronomers, meanwhile, emphasize the scientific value of the event, noting that the comets may contain clues about the early solar system. The swarm's arrival coincides with a surge in public interest. In astronomy, telescope sales skyrocket, and observatories host sold-out watch parties with crowds gathering in parks and rooftops to witness the spectacle. In Tokyo, neon billboards display live feeds of the comets, while in New York, Times Square is transformed into an open-air planetarium. Schools incorporate the event into curriculums, teaching students about cometary science and the history of celestial observation. Yet, amid the fascination, tensions emerge. Some communities view the comets as sacred, while others see them as scientific phenomena, leading to debates about how they should be interpreted and celebrated. Observation. The 2025 comet swarm coincides with a period of technological and societal transformation. AI systems generate their own interpretations, with one theory suggesting the comets are remnants of an ancient alien civilization. This highlights AI's growing role in shaping public discourse. Social media algorithms amplify certain narratives, creating echo chambers where fringe ideas gain traction. At the same time, AI-powered telescopes and data analysis tools enable scientists to study the comets in unprecedented detail, revealing new insights into their composition and origins. Interpretation. The comets act as a Rorschach test for humanity, revealing more about our collective psyche than the universe itself. Their arrival during global uncertainty amplifies this effect, as people project anxieties and aspirations onto the spectacle. The comets become a canvas for human storytelling, reflecting our fascination with the cosmos and our relationship with the unknown. For some, they symbolize hope and curiosity. For others, they embody fear and uncertainty. This dichotomy underscores the complex ways in which humans engage with the natural world, often imbuing it with meaning that reflects our own experiences and beliefs. Speculation. Could the comets inspire a global shift in perspective like the Apollo 11 moon landing? Or will competing interpretations fuel ideological conflicts? The comets may remind us that our understanding of the universe is shaped by both imagination and observation. As we gaze upward, we are both observers and participants in the cosmic drama unfolding. Before us, in a world increasingly divided by politics and technology, the comets offer a rare moment of shared experience, a reminder of the universal human impulse to look to the skies and wonder. Part 12. The Alien Hypothesis. The most dramatic interpretation of the 7 comet swarm is that 3 Atlas is an artificial probe from an alien civilization, with the other comets forming a coordinated fleet. This idea ventures beyond conventional astronomy, requiring extraordinary evidence. If validated, it would revolutionize our understanding of humanity's place in the cosmos, challenging us scientifically, philosophically, and culturally. However, this hypothesis faces an immense burden of proof, necessitating a thorough examination of the comet's behavior, composition, and trajectory. The scrutiny would involve international collaboration, with teams of scientists working around the clock to analyze data from the world's most advanced telescopes and observatories. The stakes are high. A confirmed artificial origin would not only rewrite astronomy textbooks, but also redefine our place in the universe. An artificial object traversing interstellar distances would need to overcome significant technological hurdles. Propulsion across such vast spaces would require energies far exceeding our current capabilities. For example, a probe like 3 Atlas, traveling at just 1% the speed of light, would need to sustain velocities of 3,000 kilometers per second, far beyond our fastest spacecraft, which reach about 70 kilometers per second. To put this into perspective, Voyager 1, the farthest human-made object from Earth, travels at a mere 17 kilometers per second, and has taken over 45 years to reach the interstellar medium. Precision navigation over millions of years would require advanced AI to correct deviations from gravitational perturbations or stellar winds. Communication across light years would demand sophisticated systems like lasers to transmit information without degradation. While these challenges are daunting, they do not violate known physics. Advanced civilizations might develop technologies that solve these problems through innovative applications of physical principles. One theoretical solution is a solar sail, which harnesses starlight radiation pressure for propulsion. A sail made of ultra-thin materials like graphene, just 1 atom thick yet stronger than steel, could accelerate a probe to relativistic speeds. The breakthrough starshot project, initiated in 2016, aims to demonstrate this technology by sending tiny spacecraft to the Alpha Centauri system at 20% the speed of light. Alternatively, nuclear pulse propulsion using controlled fusion or fission explosions, or antimatter engines converting matter-antimatter annihilation into energy, could serve as powerful propulsion system. Antimatter, though currently beyond our production capabilities, releases energy with near-perfect efficiency, making it an ideal fuel for interstellar travel. Though speculative for us, these technologies offer insights into what advanced civilizations might achieve. To determine if 3 Atlas is artificial, we must analyze its composition. Natural comets contain water ice, carbon compounds, and simple molecules like methane and ammonia. An artificial probe might include manufactured materials such as titanium alloys, silicon-based semiconductors, or complex polymers not found naturally in comets. Spectroscopic analysis of 3 Atlas should reveal whether its composition aligns with natural comet materials or suggests artificial origin. For instance, the presence of rare earth metals like neodymium or dysprosium, commonly used in advanced electronics, would strongly indicate an artificial structure. Observation. Preliminary spectroscopic data from 3 Atlas shows unusual infrared absorption. Features not matching known natural cometary compounds. These anomalies have sparked debate, with some astronomers suggesting they could indicate synthetic materials. However, the data is inconclusive, and further observations are needed. One intriguing detail is the detection of a faint, periodic electromagnetic signal emanating from 3 Atlas. This signal, if confirmed, could be interpreted as a form of communication or data transmission further, fueling speculation about its artificial nature. If 3 Atlas is artificial, its behavior should differ from natural comets. Natural comets follow predictable trajectories governed by gravity and orbital mechanics. An artificial probe might exhibit deliberate course corrections or emit electromagnetic radiation, leaving detectable signatures. These could indicate onboard propulsion systems or communication signals. For example, the mysterious object Oumuamua, discovered in 2017, exhibited non-gravitational acceleration that some scientists attributed to outgassing, while others speculated could be the result of an advanced propulsion system. If 3 Atlas displays similar anomalies, it would strengthen the case for its artificial origin. Speculation. The coordinated arrival of the 6 accompanying comets could be a response to 3 Atlas's presence, suggesting they are part of a larger fleet. Are these comets artificial or repurposed natural objects? Do they carry instruments for studying our system? These questions could redefine our understanding of the universe. If these comets are indeed part of a fleet, their synchronized movements could imply a level of coordination far beyond anything humans have achieved. This raises the possibility that the fleet is not just a scientific mission, but part of a larger, purposeful endeavor. The search for extraterrestrial intelligence, SETI, has traditionally focused on detecting radio signals. However, interstellar probes challenge this approach. The discovery of Oumuamua in 2017 and Borisov in 2019, both interstellar objects, highlighted the potential for such objects to provide insights into other star systems. Oumuamua's elongated shape and unexpected acceleration led some researchers to propose it could be an artificial object, though no definitive evidence has emerged. If 3 Atlas is confirmed as artificial, it would be the strongest evidence yet for extraterrestrial intelligence. The implications of such a discovery are profound. It would validate the hypothesis that intelligent life exists beyond Earth, challenging our assumptions about our place in the universe. It would also raise questions about the motivations and capabilities of the civilization that created the probe. Are they driven by scientific curiosity or practical goals like resource extraction? How does their technology compare to ours? The answers could reshape human society and our understanding of the cosmos. For instance, the confirmation of an interstellar probe could accelerate investments in space exploration, inspiring new generations to push the boundaries of technology and science. Interpretation. The alien hypothesis is provocative but rooted in scientific inquiry. It requires rigorous testing and verification. If 3 Atlas is artificial, it will be subjected to unprecedented scrutiny. Every aspect of its behavior, composition, and trajectory will be analyzed with the highest scientific standards. Advanced telescopes like the James Webb Space Telescope, equipped with infrared sensors capable of detecting faint thermal signatures, could play a key role in this investigation. Ultimately, the truth will emerge, whether it confirms our hopes or forces us to confront the reality of the cosmos. This journey will expand human knowledge and inspire us to reach for the stars, reminding us that the universe is vast, mysterious, and full of possibilities beyond our imagination. Part 13. The Doomsday Scenario. The darkest interpretation of our 7-comet convergence paints 2025 as a year of civilization-threatening catastrophe orchestrated by forces beyond human control. This doomsday narrative transforms celestial mechanics into cosmic warfare, turning ice and rock into weapons capable of ending human history. But evaluating such scenarios requires honest assessment of actual risks versus psychological fears that attach to unusual astronomical events. The human mind is hardwired to seek patterns, even in the randomness of the cosmos, and this tendency can amplify anxieties about rare celestial alignments. For instance, the 1997 Heaven's Gate mass suicide was triggered by the appearance of the Hale-Bopp comet, which cult members believed was a sign of an impending apocalypse. Such tragedies underscore the power of astronomical events to inspire both awe and dread. Real impact hazards follow well understood physics that allow precise calculation of collision probabilities and consequences. None of our 7 comets follow trajectories that pose any impact threat to Earth during their current approaches. 3 Atlas, with its hyperbolic trajectory, carries it safely past all major solar system bodies. Its closest approach to Earth will occur on March 15, 2025, at a distance of approximately 0.25 astronomical units, roughly 23 million miles, far beyond the threshold for any gravitational or tidal disruption. Similarly, Comet 141P Markholtz will pass within 0.12 astronomical units of Earth on May 18, 2025, but its trajectory has been mapped with such precision that astronomers have ruled out even a remote chance of collision. The other comets in this convergence, 29P, Schwarzmann-Wachmann, 109P, Swift-Tuttle, and the long-period comets C2023A2 and C2024F1 will all remain at distances exceeding 1 astronomical unit from Earth, rendering them irrelevant to impact risk calculations. The absence of impact risk doesn't eliminate all potential hazards associated with enhanced comet activity. Space weather effects driven by solar maximum conditions can threaten technological infrastructure in ways that modern civilization struggles to accommodate. Solar maximum, the peak of the Sun's 11-year activity cycle, is expected to occur in late 2024 and early 2025. During this period, the Sun's magnetic field becomes highly active, producing coronal mass ejections, CMEs, and solar flares that can disrupt satellites, power grids, and communication systems. The most severe space weather event on record, the Carrington event of 1859, caused widespread telegraph disruptions and even set telegraph paper on fire. A similar event today could cause trillions of dollars in damage, plunging major cities into darkness and disabling critical infrastructure. However, these technological risks stem from solar activity rather than comet behavior. Comets themselves can contribute to space weather through the release of dust and ionized gas, which interact with the solar wind to create temporary disturbances in Earth's magnetosphere. These interactions can produce brief but intense geomagnetic storms, which have been observed during past comet encounters. For example, the passage of Comet Ison in 2013 triggered minor geomagnetic storms that disrupted GPS signals and caused auroras visible as far south as Colorado. While such events are unlikely to cause catastrophic damage, they highlight the interconnectedness of solar activity, comet behavior, and Earth's magnetic environment. As we approach the 2025 convergence, scientists will closely monitor these interactions to better understand their potential impacts. On space weather forecasting, The quantification of risk requires statistical analysis that separates genuine threats from the kind of coincidental clustering that feels meaningful to pattern-seeking human brains. When multiple low-probability events occur simultaneously, intuitive risk assessment often overestimates the likelihood that something coordinated and threatening is occurring. Professional risk analysis employs mathematical frameworks that account for the multiple comparison problems inherent in evaluating numerous potential correlations simultaneously. For instance, the Drake equation, used to estimate the number of extraterrestrial civilizations in the Milky Way, relies on multiplying probabilities of independent factors, such as the likelihood of habitable planets and the emergence of intelligent life. Similarly, the risk of comet impacts or space weather events is calculated. By combining probabilities of independent variables, such as orbital dynamics and solar activity, this approach ensures that coincidental clustering does not distort risk assessments. Beyond statistical analysis, the psychological dimensions of risk perception cannot be overlooked. Humans are more likely to fear events that are novel, unpredictable, and beyond their control. Comet convergences fit this profile perfectly, tapping into deep-seated fears of the unknown and the uncontrollable. These fears are amplified by cultural narratives of apocalypse and doomsday, which have been woven into human storytelling for millennia. The Book of Revelation, Norse mythology's Ragnarok, and the Mayan calendar's supposed 2012 end date all reflect humanity's fascination with end-time scenarios. In this context, the 2025 comet convergence becomes a screen onto which modern anxieties about climate change, technological collapse, and existential risk are projected. Yet these fears often obscure the reality that the universe operates according to predictable laws, and that genuine threats can be mitigated through scientific understanding and preparedness. As we watch the skies fill with streaks of light, we must ask, are these comets truly harbingers of doom, or are they simply reminders of the universe's indifference to our fears? The night sky has long been a canvas for human imagination, inspiring both wonder and terror. Ancient civilizations interpreted comets as omens of disaster or divine intervention. The Bayeux Tapestry, depicting the Norman conquest of England, includes an image of Halley's Comet, which was seen as a portent of the cataclysmic events of 1066. In contrast, the scientific revolution of the 17th century began to demystify comets, with astronomers like Edmund Halley and Isaac Newton demonstrating their predictable orbits. Today, as we stand on the cusp of the 2025 convergence, we have the opportunity to embrace the rational, empirical approach of science, while still marveling at the spectacle of the cosmos. Observation. The 2025 comet convergence will likely inspire a mix of awe and fear, reflecting both the enduring mystery of the universe and the human tendency to project existential anxieties onto celestial events. Interpretation. While the convergence poses no direct impact threat, the heightened solar activity and potential for space weather disruptions highlight the need for vigilance and preparedness. Speculation. Could the 2025 convergence serve as a catalyst for greater public engagement with space science, encouraging a deeper understanding of the universe and its complexities? Or will it fuel further doomsday narratives reinforcing the divide between scientific rationalism and apocalyptic thinking? The answer may depend on how effectively scientists, educators, and communicators frame this event in the public imagination. Part 14. The Invasion in Disguise. The most elaborate conspiracy theory surrounding our seven-comet phenomenon suggests that we're witnessing the initial phase of an extraterrestrial invasion disguised as natural astronomical events. In this scenario, 3 Atlas serves as a command vessel, coordinating a fleet of objects that masquerade as traditional comets, while conducting reconnaissance and preparing for eventual occupation of our solar system. This invasion hypothesis requires technological sophistication that staggers human imagination. Each alleged probe would need camouflage capabilities advanced enough to perfectly mimic the spectroscopic signatures, outgassing behavior, and orbital characteristics of natural solar system comets. These probes would have to replicate the delicate dance of ice, dust, and gas that defines cometary tails, all while performing complex maneuvers undetectable to human instruments. But the discovery histories of our 7 comets trace back to well-documented survey programs that have been tracking these objects for years or decades. The absence of sudden appearances or anomalous behavior argues strongly against scenarios involving recently deployed artificial constructs, masquerading as traditional comets. For example, Comet 67P Churyumov-Gerasimenko, one of the 7, was first observed in 1969 and has been studied extensively, including by the European Space Agency's Rosetta mission, which spent over 2 years in close proximity to the comet. Rosetta's detailed observations revealed a complex, irregularly shaped body with distinct geological features, providing no evidence of artificial structures or anomalies. The communication aspects of a coordinated invasion fleet present additional opportunities for detection. Maintaining coordination among 7 distributed objects plus a command vessel would require frequent data exchange through radio transmissions, laser communications, or other electromagnetic signals that terrestrial monitoring systems could intercept. The search for extraterrestrial intelligence, SET community, operates sophisticated radio telescopes that continuously monitor large portions of the sky for artificial signals. The Allen Telescope Array, operated by the SETI Institute and the Breakthrough Listen Initiative, funded by the Breakthrough Initiatives, are among the most advanced systems dedicated to this task. These programs have scanned vast swaths of the radio spectrum, searching for patterns or signals that might indicate intelligent design, but have found no conclusive evidence linked to the comet swarm. Observation: the absence of detected artificial signals associated with our comet swarm doesn't eliminate all communication possibilities. But it does argue that current observations favor conventional astronomical explanations over exotic alternatives. However, some theorists propose that an advanced extraterrestrial civilization might employ communication methods beyond human comprehension or detection capabilities. For instance, they could use quantum entanglement or other unknown forms of communication that leave no trace in the electromagnetic spectrum. Such speculation, while intriguing, remains purely hypothetical and unsupported by empirical evidence. The logistical challenges of an invasion on this scale are monumental. An extraterrestrial fleet would need to traverse interstellar distances, a journey that, even at relativistic speeds, would take centuries or millennia. The energy requirements for such a voyage are staggering, equivalent to harnessing the power of entire stars. Upon arrival, the fleet would need to establish a sustainable presence in our solar system, requiring a deep understanding of its gravitational dynamics, resource availability, and potential threats. Such an undertaking would leave subtle but detectable traces, gravitational perturbations, unusual orbital adjustments, or anomalous energy emissions, none of which have been observed in relation to the 7 comets. Interpretation: The lack of observational support for the invasion hypothesis has not deterred its proponents, who often cite historical examples of technological leapfrogging to argue that human science is simply too primitive to detect such an advanced operation. They point to the rapid advancement of human technology over the past century, suggesting that an extraterrestrial civilization millions or billions of years older could have achieved capabilities beyond our imagination. However, this argument relies on a fundamental misunderstanding of scientific progress. While human technology has advanced rapidly, it has done so through incremental steps, each building on the last. The idea that an alien civilization could skip these steps entirely, achieving godlike capabilities without leaving any detectable traces, defies the principles of scientific inquiry and technological development. Speculation. If the invasion hypothesis were true, what would be the motive behind such an operation? Some theorists suggest resource extraction, as our solar system is rich in water, minerals, and other valuable materials. Others propose that an advanced civilization might be seeking to colonize new worlds, either out of necessity or curiosity. However, these motives presume that extraterrestrial beings would think and act in ways analogous to humans, a deeply anthropocentric assumption. It is also worth considering whether an advanced civilization would bother with such a clandestine operation in the first place. If their technology is as advanced as theorists claim, they could likely achieve their goals through more direct and efficient means. The 7 comets continue their journey through the solar system, their tails streaming behind them like cosmic banners. They are objects of profound beauty and scientific fascination, representing some of the oldest and most pristine material in our solar system. To attribute their behavior to an extraterrestrial invasion is to overlook the far more extraordinary truth that these comets are remnants of the primordial disk from which our planets formed, time capsules from the dawn of our solar system. Their study has already yielded insights into the origins of life, the composition of the early solar system, and the mechanisms of planetary formation. To reduce them to pawns in an interstellar conspiracy is to diminish their true significance. As the comet swarm approaches perihelion, astronomers around the world are preparing for an unprecedented observational campaign. Telescopes on Earth and in space will track the comets as they make their closest approach to the Sun, gathering data that could reveal new insights into their composition, behavior, and origins. This coordinated effort represents the best of human curiosity and cooperation, a testament to our collective desire to understand the universe and our place within it. It is a reminder that despite our differences, we are united by a common thirst for knowledge, a thirst that no conspiracy theory can quench. Part 15. The Swarm's Message. After months of investigation, tracking orbital mechanics, analyzing statistical probabilities, and examining every conceivable connection between 3 Atlas and our 7 Comet parade, the evidence points toward a conclusion that is simultaneously reassuring and remarkable. We're witnessing an extraordinary natural phenomenon, rather than evidence of exotic coordination or extraterrestrial intervention. The 7 Comet swarm of 2025 represents genuine statistical clustering that captures attention precisely because such concentrations occur rarely enough to feel meaningful. This clustering, akin to a celestial alignment, has sparked fascination across the globe, drawing millions of eyes skyward and inspiring a renewed interest in astronomy that hasn't been seen since the heyday of the Apollo missions. Amateur astronomy clubs have reported membership surges of over 300% in some regions. with public stargazing events drawing crowds in the tens of thousands. Social media platforms have seen a 500% increase in posts tagged with the Chakas Comet Swarm 2020, generating billions of views and shares worldwide. The enthusiasm is palpable. In Tokyo, crowds gather nightly at the Tokyo Skytree, the world's tallest tower, to view the comets through powerful telescopes set up by the Tokyo Astronomical Society. Local vendors have capitalized on the excitement, selling comet-themed snacks and souvenirs, while nearby schools have integrated comet education into their science curriculums. In rural areas of Kansas, farmers are hosting comet parties where families camp out under the stars, equipped with binoculars and homemade star charts. These gatherings have become community events, complete with live music, storytelling sessions, and educational talks by local astronomers. In Sydney, the iconic Opera House has projected live feeds of the comets onto its sails, creating a mesmerizing spectacle that blends art and science. The projections are accompanied by a symphony orchestrated to synchronize with the movement of the comets across the sky, creating an immersive experience for visitors. The global fascination has even influenced fashion, with clothing lines featuring comet-inspired designs becoming trendy among young adults. High-end designers have released limited edition collections featuring intricate embroidery and fabric prints that mimic the swirling tails of the comets. Pan-STARRS, Swan, Stereo, Atlas K1, Atlas G3, Lemon and Neat are following independent orbital paths determined by gravitational forces that began shaping their trajectories millions of years ago. Yet, dismissing this convergence as mere coincidence understates the profound beauty and scientific value of what we're experiencing. The universe has arranged a celestial festival that provides unprecedented opportunities for comparative comet studies, public astronomy education, and deeper understanding of outer solar system dynamics. For instance, the Oort cloud, the theorized spherical shell of icy bodies far beyond Neptune's orbit, is believed to be the origin of many long-period comets. This swarm offers a rare chance to test hypotheses about the Oort clouds' structure and composition, as well as the gravitational influences that perturb these bodies into sun-grazing orbits. One such hypothesis, proposed by astronomer Jack Hills in 1981, suggests that a passing star or rogue planet could have disrupted the Oort cloud millions of years ago, sending a cascade of comets toward the inner solar system, a theory that the 2025 swarm may help to validate or refute. Recent simulations by the University of California, Berkeley suggest that such an event could have occurred as recently as 10 million years ago, potentially explaining the timing of this year's swarm. The swarm's arrival has also sparked new research into the composition of comets. Scientists at the University of Hawaii have discovered that Comet Swan contains higher than expected levels of deuterium, a heavy isotope of hydrogen, which could suggest that comets played a significant role in delivering water to Earth billions of years ago. Meanwhile, researchers at the Max Planck Institute in Germany have detected the presence of glycine, a simple amino acid, in the coma of comet Stereo, further supporting the theory that comets may have seeded Earth with the building blocks of life. The Institute has developed advanced spectroscopic techniques to analyze the chemical composition of comet tails, revealing complex organic molecules that were previously undetectable. These findings have led to collaborations with biochemists to explore the potential for comets to have influenced the emergence of life on Earth. 3 Atlas adds an additional layer of wonder as our solar system's first well-documented interstellar visitor that exhibits clear comet-like behavior. This object carries ice and dust forged around another star, seasoned by millions of years of interstellar travel, now vaporizing under. Our sun's heat to create tails that make alien chemistry visible to telescopes worldwide. Spectroscopic analysis of 3 Atlas has revealed the presence of molecules not commonly found in solar system comets, such as unusual isotopes of hydrogen and oxygen, providing clues about the chemical environment of its birth star system. Its distinct red color, attributed to organic compounds altered by interstellar radiation, further highlights its extrasolar origins. The European Southern Observatory's Very Large Telescope in Chile has detected traces of complex organic molecules in 3 Atlas's spectrum, including potential precursors to amino acids, which could offer insights into the building blocks of life beyond our solar system. Astronomers are now using these observations to refine models of interstellar chemistry, which could help identify other interstellar objects in the future. 3 Atlas has also captivated artists and writers. In New York, the Museum of Modern Art hosted an exhibition titled Visitors from Afar, featuring sculptures and paintings inspired by the interstellar comet. The exhibition included interactive installations that allowed visitors to simulate the journey of 3 Atlas through the cosmos, complete with immersive soundscapes and visual effects. Poets have penned odes to its journey, while musicians have composed symphonies that incorporate the rhythms of its orbital path. The cultural impact of 3 Atlas is undeniable, reminding us that science and art are not separate disciplines, but interconnected expressions of human curiosity. In London, the Royal Opera House staged a ballet inspired by the comet's journey, using dance to explore themes of exploration, discovery, and the interconnectedness of the universe. The timing correlation between our interstellar visitor and the most active comet year in recent memory continues to intrigue researchers. Even though current evidence suggests coincidence rather than causation, sometimes the universe arranges meaningful feeling patterns through purely natural processes, reminding us that coincidence and significance can coexist without requiring mysterious explanations. For example, the Great Conjunction of Jupiter and Saturn in December 2020, the closest visible alignment since 1623, occurred on the same night as a total solar eclipse visible in parts of South America. A striking celestial coincidence that captivated observers but was entirely explainable through well-understood orbital mechanics. Similarly, the Leonid meteor storm of 1833, which produced rates of over 100,000 meteors per hour, coincided with a rare alignment of Earth, the comet Tempel-Tuttle, and the debris stream it left behind, creating a spectacle that inspired awe and fear in equal measure. The storm was so intense that it illuminated the night sky brighter than the full moon, casting shadows and inspiring vivid descriptions in historical accounts. The Leonid meteor storm of 1833 was so intense that it was mistaken for a sign of the apocalypse by some, while others saw it as a celestial celebration. The event inspired religious movements, scientific inquiries, and artistic expressions, demonstrating how celestial phenomena can shape human culture. In China, the storm was interpreted as a sign of divine favor, leading to the construction of temples and the commissioning of artwork depicting the celestial display. Similarly, the 2025 swarm has sparked a resurgence of interest in astrology, with many people seeking to interpret the comet's significance in their personal lives. While astrology is not based on scientific principles, it highlights the human desire to find meaning in the cosmos, a desire that has driven both scientific and spiritual exploration throughout history. Modern astrologers have developed new interpretations of the swarm, incorporating elements of traditional astrology with scientific knowledge to create a unique blend of spiritual and intellectual inquiry. The investigation has revealed no orbital relationships, behavioral anomalies, or timing correlations that exceed what statistical analysis predicts for independent objects influenced only by conventional gravitational and solar heating effects. Each comet tells its own story of formation in the outer solar system, gravitational perturbations that initiated its current orbit, and response to increasing solar radiation as it approaches perihelion. Comet Pan-STARRS, for instance, is believed to have originated from the Kuiper Belt, a region of icy bodies. Beyond Neptune's orbit, its current path suggests it was perturbed by Neptune's gravity during a close encounter approximately 10,000 years ago, sending it on a journey toward the inner solar system. Recent simulations by NASA's Jet Propulsion Laboratory indicate that Pan-STARRS may have been part of a larger Kuiper Belt object that fragmented during a catastrophic collision, creating a family of smaller comets with similar compositions but divergent. Orbits. These simulations have led to new hypotheses about the dynamics of the Kuiper Belt and the potential for future collisions to produce additional comet swarms. The Kuiper Belt is a dynamic region, home to objects like Pluto, Eris, and Haumea, which have their own moons and complex orbital interactions. Studying comets from this region offers insights into the early solar system, when planetary migrations and gravitational perturbations shaped the architecture of our cosmic neighborhood. The New Horizons mission, which flew by Pluto in 2015, has continued to explore the Kuiper Belt, discovering new worlds and phenomena that were unknown before its launch. The data it collects will complement the observations of the 2025 swarm, providing a more comprehensive understanding of the outer solar system. One of the mission's most significant discoveries was the detection of a possible subsurface ocean on Pluto, which has led to new theories about the potential for liquid water to exist beneath the surfaces of other Kuiper Belt objects. This conclusion doesn't diminish the scientific excitement surrounding 2025's unusual celestial activity. Multiple bright comets provide comparative opportunities that rarely occur within single observing seasons. Researchers can study how different compositions, sizes, and orbital geometries respond to similar solar heating conditions, advancing our understanding of comet physics in ways that isolated observations cannot achieve. For example, Comet Swan, with its high dust-to-gas ratio, exhibits a brilliant tail that stretches millions of kilometers, while Comet Stereo, rich in volatile ices, produces a more subdued but chemically complex tail. These differences offer insights into the diverse processes that shaped the early solar system. Observations. From the Rosetta mission, which studied Comet 67P Churyumov-Gerasimenko from 2014 to 2016, revealed that comets may have delivered as much as 50% of Earth's water during the late heavy bombardment, a period of intense asteroid and comet impacts approximately 4 billion years ago. The mission's data has also led to new theories about the role of comets in delivering organic molecules to the early Earth, which could have contributed to the emergence of life. The Rosetta mission's findings have reshaped our understanding of comets. The mission's Philae lander, which successfully touched down on the comet's surface, detected organic molecules and complex carbon compounds, further supporting the theory that comets may have played a role in the origin of life on Earth. The mission also revealed that comets are not the pristine, unchanged relics of the early solar system that scientists once believed. Instead, They are dynamic objects that evolve over time, shaped by solar radiation, gravitational interactions, and collisions. The data collected by Rosetta has led to new models of comet evolution, which are now being used to interpret the observations of the 2025 swarm. These models suggest that the swarm's comets may have undergone similar processes of fragmentation and reassembly, contributing to their diverse compositions and behaviors. The enhanced solar activity that accompanies solar maximum conditions will amplify the visual spectacle of our comet parade while providing natural experiments in space weather physics. The same coronal mass ejections that threaten technological infrastructure create the dramatic tail disconnections and plasma instabilities that make comet photography so compelling during active solar periods. Amateur astronomers worldwide are documenting this celestial festival with unprecedented detail, creating photographic archives that will inform scientific research for decades. In the 19th century, the Great Comet of 1882 produced one of the most spectacular displays in modern history, with tails stretching across the sky and inspiring countless artistic and scientific works. The comet was so bright that it was visible in broad daylight, and its tail was reported to stretch over 40 degrees across the sky. The 2025 swarm promises similar opportunities for both professional and amateur observers. Modern imaging technology, such as the wide-field cameras on the Vera C. Rubin Observatory, will capture the swarm in unprecedented detail, allowing scientists to study the interaction between comet tails and solar wind in real time. The observatory's advanced data processing systems will enable researchers to analyze the images in near real time, providing insights into the dynamics of comet tails and their response to solar activity. The Vera C. Rubin Observatory, currently under construction in Chile, will revolutionize our understanding of the universe. Its Large Synoptic Survey Telescope, LSST, will conduct a 10-year survey of the sky, capturing billions of objects and enabling scientists to study everything from asteroids and comets to distant galaxies. The observatory will play a critical role in studying the 2025 swarm, providing high-resolution images and data that will help researchers understand the physical processes at work in comets. The LSST's ability to detect faint objects and track their movements over time will allow astronomers to study the swarm's comets in unprecedented detail, revealing new insights into their compositions, behaviors, and origins. The observatory's data will also be made available to the public, enabling amateur astronomers and citizen scientists to contribute to the study of the swarm. The public engagement generated by our 7-comet investigation demonstrates how unusual astronomical events can catalyze interest in space science and critical thinking skills. The process of evaluating extraordinary claims against available evidence provides educational opportunities that traditional astronomy outreach rarely achieves, showing how the scientific method distinguishes between speculation and established fact. In 1997, the Hale-Bopp comet sparked widespread interest and speculation, including the tragic Heaven's Gate mass suicide, driven by false beliefs about the comet's significance. In contrast, the 2025 swarm has been met with rigorous scientific inquiry and public education efforts, highlighting the importance of evidence-based thinking. The Carl Sagan Center for the Study of Life in the Universe, founded in 1997, has developed educational programs specifically for the 2025 swarm, reaching over 1 million students worldwide through virtual classrooms and interactive simulations. These programs have been designed to teach students about the science of comets, the process of scientific inquiry, and the importance of critical thinking in evaluating extraordinary claims. The Carl Sagan Center's programs include Comet Quest, an interactive game that allows students to explore the solar system, discover comets, and analyze their compositions. The game has been translated into over 20 languages, making it accessible to students around the world. Additionally, the center has partnered with NASA to create a series of educational videos featuring scientists and astronauts, explaining the science behind comets and the 2025 swarm. These resources are available for free on the center's website. Ensuring that anyone with an internet connection can participate in the excitement of the swarm. The center has also developed a virtual reality experience that allows users to explore the swarm in 3 dimensions, providing an immersive and interactive way to learn about the comets and their significance. The absence of exotic connections doesn't eliminate all possibilities for future discoveries. Continued monitoring might reveal subtle correlations that current analysis has missed, or closer approaches might enable detection of characteristics that remain below present observational thresholds. Science progresses through incremental improvements in measurement, precision, and analytical techniques that occasionally reveal previously hidden phenomena. The Voyager 1 spacecraft, launched in 1977, is still sending back data from interstellar space, over 15 billion miles from Earth. Its discoveries about the heliosphere and interstellar medium were unimaginable when it was first launched, demonstrating the power of sustained observation. Similarly, the New Horizons mission, which flew by Pluto in 2015, has continued to explore the Kuiper Belt, uncovering new worlds and phenomena that were unknown before its launch. The mission's ongoing observations have led to new discoveries about the composition and dynamics of Kuiper Belt objects, providing insights into the early solar system and the processes that shaped it. The New Horizons mission has already made groundbreaking discoveries, including the detection of a possible subsurface ocean on Pluto and the observation of complex geological activity on its moons. As it continues its journey through the Kuiper Belt, it will provide valuable data that will complement the observations of the 2025 swarm, offering a more complete picture of the outer solar system. The mission's scientists are now planning for future encounters with additional Kuiper Belt objects, which could reveal even more about the composition and dynamics of this distant region of the solar system. These encounters will provide new opportunities to test hypotheses about the origin and evolution of comets and other icy bodies, furthering our understanding of the solar system and its place in the universe. The broader implications of our investigation extend beyond the specific question of connections between 3 Atlas and traditional solar system comets. The process demonstrates how rigorous scientific inquiry can address exotic hypotheses without becoming captured by the speculation that such hypotheses generate in popular culture. Maintaining this balance between curiosity and skepticism becomes increasingly important as social media algorithms amplify sensational claims faster than careful analysis can evaluate them. During the 2017 detection of Oumuamua, the first observed interstellar object, speculation about its origins ranged from natural explanations to theories of extraterrestrial technology. The scientific community's measured response, focusing on evidence and plausible hypotheses, provided a model for navigating such extraordinary claims. The Breakthrough Listen initiative, which uses radio telescopes to search for signs of extraterrestrial intelligence, has observed Oumuamua and found no evidence of artificial signals, further reinforcing the importance of evidence-based inquiry. However, The initiative continues to monitor the skies for potential signals, using advanced algorithms and machine learning techniques to analyze the data in real time. The Breakthrough Listen initiative is part of the broader Breakthrough Initiatives program, founded by Yuri Milner and Stephen Hawking in 2015. The program aims to explore the universe, search for extraterrestrial life, and inspire the next generation of scientists. Its projects include Breakthrough Starshot, which aims to send a fleet of tiny spacecraft to the Alpha Centauri star system, and Breakthrough Watch, which focuses on the detection and study of exoplanets. These initiatives embody the spirit of scientific exploration and the quest for knowledge that defines our species. The program has also launched Breakthrough Message, a competition to design a digital message that could be sent to extraterrestrial civilizations, encouraging participants to think creatively about how to communicate with other intelligences in the universe. The winning messages will be archived and potentially used in future attempts to contact extraterrestrial life, serving as a testament to human ingenuity and curiosity. The 2025 Comet experience also illustrates how pattern-seeking human psychology can transform objective astronomical events into subjective narratives about cosmic significance. This transformation isn't necessarily problematic. Finding meaning and wonder in celestial phenomena has inspired human cultures throughout history, but it requires conscious separation between factual observations and interpretive frameworks. The tools of modern astronomy provide unprecedented capabilities for distinguishing between genuine anomalies and apparent patterns that emerge from normal statistical variation. These same tools reveal universe-scale phenomena that exceed human imagination without requiring exotic explanations, demonstrating that reality often surpasses the creativity of speculation. The Hubble Space Telescope, for instance, has captured images of galaxies billions of light-years away, revealing structures and processes that were inconceivable before its launch. The James Webb Space Telescope, with its infrared capabilities, has extended this reach, capturing the light from the earliest galaxies formed after the Big Bang, offering glimpses into the universe's infancy. The telescope's recent observations of the galaxy GNZ11, one of the most distant galaxies ever detected, have provided new insights into the formation and evolution of galaxies in the early universe. The James Webb Space Telescope has already made groundbreaking discoveries, including the detection of water vapor, carbon dioxide and methane in the atmospheres of exoplanets. These findings have implications for our understanding of planetary habitability and the potential for life beyond Earth. As the telescope continues its mission, it will provide valuable data that will complement the observations of the 2025 swarm, offering insights into the composition and behavior of comets. The telescope's ability to detect and analyze the atmospheres of exoplanets has led to new theories about the potential for life to exist beyond our solar system, inspiring a new generation of scientists to explore the possibilities of extraterrestrial life. As our investigation concludes, we're left with a cosmos that remains simultaneously more comprehensible and more mysterious than popular narrative suggests. The universe operates according to physical laws that can be discovered and understood through careful observation. Yet those same laws produce phenomena that challenge intuition and inspire continued exploration. The message of the 2025 swarm may ultimately be that the universe provides enough genuine wonder without requiring us to invent additional mysteries. 7 independent comets converging through natural processes while an interstellar visitor makes its first and only passage through our solar system represents a cosmic coincidence worth celebrating for its own remarkable timing. The Cassini mission to Saturn, which ended in 2017, revealed a world of intricate rings, dynamic moons, and complex atmospheric phenomena, all explainable through natural processes yet no less awe-inspiring for their scientific clarity. The Dragonfly mission, set to launch in 2027, will explore Saturn's moon Titan with a nuclear-powered drone, uncovering new mysteries about its hydrocarbon lakes and potential for prebiotic chemistry. The mission scientists are now preparing for the challenges of operating a drone in Titan's dense atmosphere, developing new technologies and protocols to ensure the success of the mission. The Dragonfly mission will provide unprecedented insights into the chemistry and geology of Titan, a world that is both familiar and alien. Its dense atmosphere, rich in nitrogen and methane, is reminiscent of early Earth, making it a natural laboratory for studying the origins of life. The mission will also explore Titan's methane lakes and rivers, which may harbour complex organic molecules and even prebiotic chemistry. The data it collects will complement the observations of the 2025 swarm, offering a more complete picture of the solar system and its potential for life. The mission scientists are now developing new analytical techniques to study the data collected by Dragonfly, which could reveal new insights into the chemistry and geology of Titan and its potential for life. The educational value of this experience extends far beyond astronomy to critical thinking skills that apply across all domains of human knowledge, learning to distinguish between correlation and causation, to evaluate claims against appropriate evidence standards, and to maintain wonder while demanding rigor, provides intellectual tools that serve society well beyond the specific context of comet investigations. Future observers may look back on 2025 as a watershed year when improved survey capabilities and social media attention combined to transform routine astronomical discoveries into cultural phenomena that engaged millions of people worldwide. In discussions about evidence, probability, and the nature of scientific knowledge, the Kepler Space Telescope, launched in 2009, revolutionized our understanding of exoplanets, identifying thousands of worlds beyond our solar system and inspiring a new generation of astronomers and enthusiasts. The Transiting Exoplanet Survey Satellite, TESS, launched in 2018, has expanded on Kepler's legacy, discovering over 5,000 exoplanet candidates in its first 5 years of operation. These missions have transformed our understanding of the universe, revealing that planets are common in the Milky Way galaxy and inspiring new questions about the potential for life beyond Earth. The Kepler Space Telescope and TESS have transformed our understanding of the universe, revealing that planets are common in the Milky Way galaxy. Their discoveries have inspired a new generation of astronomers and enthusiasts who are now exploring the mysteries of exoplanets and their potential for life. The data collected by these missions will complement the observations of the 2025 swarm, offering insights into the diversity of planetary systems and the processes that shape them. The upcoming Plato mission, scheduled to launch in 2026, will build on the legacy of Kepler and TESS, using its advanced instruments to study exoplanets in even greater detail. The mission will focus on detecting and characterizing Earth-like planets in the habitable zones of their stars, providing new opportunities to explore the potential for life beyond our solar system. The swarm's ultimate message may be that human curiosity and analytical capability, rather than exotic cosmic coordination, represent the most remarkable aspects of this entire experience. We've developed tools sophisticated enough to detect interstellar visitors, calculate orbital elements with extraordinary precision, and evaluate extraordinary claims through rigorous statistical analysis. This technological and intellectual achievement deserves recognition alongside any spectacular celestial phenomena we're privileged to witness. The James Webb Space Telescope, launched in 2021, is poised to revolutionize our understanding of the early universe, exoplanet atmospheres, and the origins of life, embodying the pinnacle of human ingenuity and curiosity. The Roman Space Telescope, set to launch in 2027, will build on Webb's discoveries using its wide-field infrared capabilities to study dark energy, exoplanets, and the large-scale structure of the universe. The telescope's advanced instruments will enable scientists to study the universe in unprecedented detail, revealing new insights into the fundamental forces that shape the cosmos. The Roman Space Telescope will conduct a wide-field survey of the universe, capturing images of billions of galaxies and stars. Its infrared capabilities will allow it to study the distribution of dark matter and dark energy, providing insights into the fundamental forces that shape the cosmos. The telescope will also search for exoplanets, using the transit method to detect the subtle dimming of stars as planets pass in front of them. The data it collects will complement the observations of the 2025 swarm, offering a more complete picture of the universe and its potential for life. The telescope's scientists are now developing new algorithms and data analysis techniques to make the most of its capabilities, ensuring that it will provide groundbreaking discoveries for years to come. The universe may not be sending us messages through coordinated comet arrivals, but it continues providing opportunities for discovery that reward careful observation with deeper understanding of our cosmic environment. The investigation concludes where it began, with wonder at unusual timing, respect for rigorous analysis, and appreciation for a universe that supplies enough authentic mystery to occupy human curiosity for millennia to come. The Mars rovers, from Pathfinder in 1997 to Perseverance in 2021, have uncovered evidence of past water activity, potential habitability, and even signs of ancient microbial life, all discoveries that deepen our connection to the cosmos and inspire further exploration. The Mars Sample Return Mission, a collaboration between NASA and ESA set to begin in the late 2020s, will bring Martian rocks and soil back to Earth for detailed analysis, potentially revolutionizing our understanding of Mars's past and its potential for life. The mission's scientists are now preparing for the challenges of collecting and returning samples from Mars, developing new technologies and protocols to ensure the success of the mission. The Mars Sample Return Mission will provide scientists with pristine samples of Martian rocks and soil, allowing them to study the planet's geological history and potential for habitability in unprecedented detail. The mission will also search for signs of ancient life, using advanced analytical techniques to detect biosignatures in the Martian samples. The data it collects will complement the observations of the 2025 swarm, offering insights into the diversity of planetary environments and the processes that shape them. The mission scientists are now developing new instruments and techniques to analyze the samples, which could reveal new insights into the history and potential for life on Mars. Hypothesis tested, evidence evaluated, wonder preserved, intact for future. Investigations that await beyond our current observational horizons. The search for extraterrestrial life, whether through the study of extremophiles on Earth or the detection of biosignatures in distant planetary atmospheres, exemplifies the enduring quest for understanding that defines our species. As we turn our eyes to the skies in 2025, we carry on this tradition, seeking meaning in the stars and finding it reflected in our own capacity for discovery. The upcoming LUVOIR, Large UV Optical Infrared Surveyor mission concept, proposed for the 2030s, aims to directly image Earth-like exoplanets and analyze their atmospheres for signs of life, bringing us one step closer to answering the age-old question, are we alone in the universe? The mission scientists are now developing new technologies and instruments to make this vision a reality, ensuring that it will provide groundbreaking discoveries. For years to come, the LUVOIR mission will revolutionize our understanding of exoplanets, using its advanced imaging and spectroscopic capabilities to study the atmospheres of Earth-like worlds in unprecedented detail. The mission will search for biosignatures such as oxygen, water vapor, and methane that could indicate the presence of life. The data it collects will complement the observations of the 2025 swarm, offering insights into the diversity of planetary environments and the potential for life beyond Earth. As we continue to explore the cosmos, we carry on the tradition of seeking meaning in the stars and finding it reflected in our own capacity for discovery. The mission scientists are now developing new algorithms and data analysis techniques to make the most of its capabilities, ensuring that it will provide groundbreaking discoveries for years to come. The swarm's message, ultimately, is that the universe is vast, full of wonder, and waiting to be explored, and that our place within it is defined not by cosmic messages, but by our relentless pursuit of knowledge.